Hello and welcome. Today, we delve into a story of ingenuity hidden behind the chaos of wartime shipbuilding. A story about a humble welder in 1941 who believed there had to be a better way to build ships faster and stronger. Imagine a man, earning just $11 a day, quietly sketching revolutionary ideas in a battered notebook amidst the clang of scaffolding and the flicker of welding torches. Convinced that archaic methods, like endless bolting and tedious assembly, were madness in an age of rapid war. What if installing deck planks took a dozen workers a whole week, just to secure a few feet of wood? Could welding support studs directly onto steel from above, eliminating scaffolding and slowness? Was it possible to weld in all positions, horizontal, vertical, overhead, without flux powder falling off? And might a ceramic cap hold the flux securely, making stud welding faster, stronger, and cheaper? How did a man dismissed by the Navy and ignored by engineers, who faced bureaucratic roadblocks and months-long approval processes, turn his simple idea into a wartime revolution? Could a single invention, welded studs, produced in seconds, save 50 million man-hours, accelerate ship production, and turn the tide of history? This is the story of Ted Nelson, a man who refused to accept the status quo, risking everything to build a device that would transform naval construction. How did he go from a struggling welder to a key contributor in producing thousands of submarines, aircraft carriers, and cargo ships at unprecedented speeds? And what does his journey teach us about innovation, about the power of persistence, bold ideas, and challenging authority, especially when lives and history hang in the balance? Because here's the truth. The most profound breakthroughs often begin with quiet determination, a simple question, isn't there a better way? And the courage to pursue it. The next revolutionary idea might just be waiting in a garage or a workshop, ready to change the world. And now, the story begins. In the month of March, in the year 1941, within the bustling confines of the Mayer Island Naval Shipyard situated in the city of Vallejo, California, a particular scene unfolded that captured both the labor and aspiration linchpins of the era. Amid the irregular flickering of a welding torch, casting a faint glow in the otherwise subdued atmosphere of a submarine construction bay, Edward Nelson, a humble but dedicated welder earning just $11 per day, meticulously documented his thoughts and frustrations in a well-worn notebook that had seen better days. He was compelled to think that there simply had to be a better way to accomplish the tasks at hand, something more efficient, more practical, and that the current methods, which seemed almost archaic, were nothing short of madness. Despite the pressing demands of wartime urgency, the supervising officers of the Navy persistently urged him to accelerate his pace, pushing for increased productivity, yet remained deaf to the potential solution he and possibly others had been contemplating. As he moved through the intricate maze of scaffolding that somehow supported the large wooden deck of a frigate still under construction, Nelson's eyes caught a sight that infuriated him to the core. He observed that a dozen workers were consumed by an entire shift just to install a single segment of deck planking, a task that today would seem routine but at that time consumed considerable resources. Enormous scaffolding structures dominated the interior compartments beneath each wooden deck, extending high and wide to reach the levels necessary for the workers' tasks. Inside these tight, constricted spaces, men with wrenches diligently twisted nuts onto bolts that pierced through steel girders from above, their movements slow and deliberate. Hours, often entire work shifts, were spent securing thin wooden planks to heavy steel frames in what seemed to Nelson to be a painfully inefficient process. The age-old technique demanded a level of precision, patience, and painstaking effort that, given the burgeoning war efforts and looming international conflicts, was simply a luxury that America could ill afford. At that moment, Nelson saw firsthand how antiquated practices persisted unchanged, despite the rapid development of other sectors of industry. It was startling to him that, in what was soon to be one of the busiest and most vital shipbuilding yards in the world, the methods of attachment for vital components remained largely the same as they had been for decades: slow, labor-intensive, and fundamentally inefficient. The man at the heart of this scene was Theodore Edward Nelson, a Californian by birth and pride. At 36 years of age, Nelson had earned his mechanical expertise the hard way, through 15 years of hands-on experience in various machine shops scattered across the state of California. He had learned the ins and outs of metal behavior, how electricity circulated through complex circuits, and how to troubleshoot problems if one was observant enough to spot them. Through these years, Nelson had gained a keen understanding of machinery, not merely as a worker but as an innovator who believed that solutions to the industry's toughest challenges existed if only someone would dare to look differently. Unbeknownst to many of his superiors, Nelson had already devised an alternative approach, an idea that could revolutionize the way submarines and other ships were assembled. Unfortunately for Nelson, these insights had been met with rejection, dismissed outright by the very authorities who should have appreciated ingenuity. What Nelson was unaware of at the time was that his simple yet ingenious idea, overlooked and ignored during those crucial early moments, would eventually prove to be enormously beneficial. It would save the United States Navy more than 50 million man-hours and result in a fundamental transformation of naval construction procedures across the board. The seeds of this transformation were sown weeks earlier, deep beneath the decks in the interior spaces where the true war against inefficiency was waged on a daily basis. This quiet, relentless battle against time and waste was a secret battleground, an ongoing fight to improve the speed, safety, and productivity of shipbuilding operations. The date that marked a turning point in this journey was March 15, 1941, the eve of what would soon become a pivotal moment in history. Just over 8 months before Japan's surprise attack at Pearl Harbor, the Mayer Island Naval Shipyard sprawled across 635 acres along the banks of the Napa River in Vallejo, California, a mere 25 miles northeast of San Francisco. Originally established in the year of 1854 by Commander David Glasgow Farragut, who would later become a legendary figure in naval history, this shipyard was the first United States Navy base to be founded on the Pacific Ocean. By the dawn of 1941, it had evolved into the preeminent submarine construction facility on the West Coast, serving as a vital hub for naval readiness in the Pacific Theater. The yard operated tirelessly around the clock, 3 shifts of workers swapping roles from dawn until dusk, 7 days a week, reflecting the urgency of the times. The rapid escalation of submarine construction was driven by the intensifying tensions with Japan, which threatened to plunge the world. The problem seemed to be omnipresent, evident wherever he looked, from the intricate process of installing wooden deck planking on submarines to the much larger tasks on destroyers and aircraft carriers. The Navy's choice to use wooden decks was influenced by several practical reasons, each carefully considered. Wood offered superior grip compared to steel in wet conditions, reducing the risk of crew slipping during operations. Additionally, wooden surfaces were quieter, helping minimize noise that could give away a vessel's position, thus offering a tactical advantage. Wood also provided some natural insulation against the chilling steel beneath, which was especially important in the harsh environments of maritime service. Moreover, in cases where damage to the deck occurred, wooden panels could be more straightforwardly repaired or replaced, unlike welded steel plates, which required welding expertise and more complex procedures. However, despite these benefits, the method of installing these wooden decks remained hopelessly outdated, labor-intensive, and painfully slow. The process, unchanged since the era of the First World War, consisted of a series of complicated, meticulous steps that stretched the limits of patience and stamina for the workers involved. Initially, workers would drill precise holes at fixed intervals through the wooden planks, ensuring perfect placement for fastening. These holes were then countersunk so that the heads of the bolts would sit flush with the surface of the deck, providing a smooth, level finish. Once the holes were prepared, the next step involved carefully positioning the planks onto the underlying steel framework. This stage was only the beginning of a much more laborious task. The real challenge was the construction of a complex scaffolding system beneath the deck within the confined spaces of the vessel's interior. Multiple levels of scaffolding had to be erected to give workers access to the underside of the steel deck, often inside narrow compartments that were barely 4 feet high. Creating this structure was time-consuming, requiring at least 2 days solely for its assembly, followed by another day just to dismantle it once the work was finished. With the scaffolding in place, work could proceed, but it was far from simple. Workers above and below coordinated tightly, as long threaded bolts had to be inserted through the wooden planks and aligned perfectly with matching holes in the steel framework beneath. Those working underneath, often in dark, cramped conditions on delicate platforms, would extend the bolts down through the deck. They then had to pass nuts onto the protruding ends and tighten them with wrenches, a painstaking task further complicated by the confined space and the manual effort needed to pull the planks tightly against the steel structure to ensure stability. The final touch was to fill the countersunk holes with wooden plugs, which served to smooth out the surface and prepare the deck for use. Every section of the deck received this meticulous treatment, resulting in a deck that, while functional, was a testament to slow, effortful craftsmanship. On a submarine, hundreds of square feet of decking might require thousands of individual attachment points, each one installed by hand. For larger vessels like aircraft carriers, the sheer scale increased the challenge exponentially, covering tens of thousands of square feet of deck space, a staggering amount of labor and coordination necessary to complete the task. Typically, the installation of a submarine deck demanded a team of between 12 and 16 men, working diligently for anywhere from 5 to 7 days. The construction of scaffolding alone would take 2 full days, with another single day devoted to its removal. The rest of the time was consumed with the bolts and nuts, which had to be installed precisely, tightening each one by hand to ensure the deck was firmly secured. Ted Nelson, who had performed this demanding work countless times, knew the process intimately. He had spent many hours standing precariously on scaffolding platforms, threading nuts onto bolts in the cramped confines of submarine compartments that stood barely 4 feet high. The constant bending caused his back to ache, and his knuckles bore scars from slipped wrenches and failed attempts to tighten stubborn nuts. His patience was nearly exhausted after years of such routine labor. Yet, Nelson's discontent was not solely rooted in physical discomfort. It was driven by a broader understanding of the bigger picture. He recognized that war was imminent, a fact universally acknowledged around Mare Island. The yard's schedule was already lagging, submarines and other vessels were falling behind, their construction delayed by the slow, outdated deck installation processes. Time was slipping away, and every day of delay meant fewer ships ready in the water, fewer assets to defend or attack. Each passing day brought the country closer to conflict, a reality that weighed heavily on Nelson's mind. America, he understood with growing urgency, was simply not prepared for what lay ahead. There had to be a better way, Something more efficient, more scalable, that could speed up the process without sacrificing quality or safety. For months, Nelson had been contemplating the problem, searching for innovative solutions that could overhaul the archaic methods. He knew that to meet the demands of modern naval warfare, the industry had to evolve beyond the slow, painstaking manual procedures of the past. For months, Nelson found himself mentally wandering over his repetitive welding tasks, pondering potential improvements during the endless hours spent sinking metal together on the shipyard's assembly lines. The solution, in his view, had always appeared to be uncomfortably close and remarkably straightforward. It suddenly made perfect sense to him. Instead of the complex process of bolting components from above and threading nuts from below, why not directly weld mounting studs onto the steel framework itself? This approach would be a game changer. The idea was startling in its simplicity. Instead of relying on nuts and bolts, which necessitated getting beneath the structure to tighten and secure, Nelson envisioned welding these supports directly onto the steel surfaces from only one side, namely, from above. Such a method would eliminate the need for scaffolding and the complications associated with working in confined spaces below decks. It would mean fewer workers cramped into tight compartments, less time lost maneuvering heavy equipment, and a faster, more reliable process since permanent welds are inherently stronger and more durable. At the core of this concept was the use of threaded studs. These are essentially bolts without heads, that could be swiftly welded onto the steel deck with minimal effort. These studs would serve as anchors to which wooden planks or other parts could be attached later, using threaded inserts or specialized nuts. The entire operation could be executed solely from the ship's upper surfaces, drastically reducing the logistical hurdles traditionally associated with welding or fastening in hard-to-reach places. Furthermore, because the studs would be welded directly from above, there would be no need for scaffolding, no necessity to coordinate between separate crews working on different levels, and no requirement for cumbersome operations on the lower decks. Nelson had seen a limited form of stud welding in practice before, primarily on flat, horizontal steel surfaces, where a flux powder was placed on the steel, and then a stud was fused to it by an electric arc. The flux powder, in these cases, would melt and facilitate the weld, but only on horizontal surfaces. However, this existing method posed a significant problem because it could not be reliably performed on vertical or overhead surfaces. The flux powder simply fell off the moment the welding was attempted on such surfaces, rendering the process ineffective for shipbuilding or naval construction where welding in various orientations is often essential. For over 20 years, this limitation had puzzled welding engineers worldwide. How could the process be adapted to work in all positions, horizontal, vertical, and overhead? Nelson believed he had discovered the answer, something so elegant that he nearly laughed at the simplicity of it when it presented itself. His idea was to enclose the flux within a small ceramic cap at the end of each stud. By attaching this ceramic cap to the top of the stud, the flux would be held securely in place no matter the welding orientation. This simple modification meant that the flux wouldn't fall off when welding on vertical or overhead surfaces, solving a problem long thought insurmountable. He quickly sketched his concept in his notebook: a portable, handheld welding gun equipped with a spring-loaded mechanism to press the stud against the steel surface. An electrical trigger would initiate the arc, melting the flux contained within the ceramic cap and welding the stud seamlessly onto the steel. Because the flux would remain fixed in place, the process would take less than a second per stud, an astonishing efficiency compared to the traditional bolt installation process. Nelson was confident that a single welder could lay dozens of these studs in the time it previously took to bolt one connection, thus revolutionizing the speed and labor efficiency of ship construction. Eager to share his innovative idea, Nelson approached his supervisor, a Navy lieutenant named Morrison. Their meeting was brief, scarcely lasting 5 minutes. Morrison barely glanced at Nelson's sketches, displaying an evident preference for established procedures. "We have established methods," he said curtly. "We adhere strictly to Navy specifications." His dismissive attitude made it clear that any deviation, no matter how promising, would not be entertained without formal approval. Not discouraged, Nelson then sought out the shipyard's chief welding engineer, a civilian contractor named Hartwell. He explained the potential benefits, significant time savings, reductions in labor requirements, and the possibility of eliminating costly scaffolding and other equipment. Hartwell listened politely but remained largely indifferent. "Son," he told Nelson, "many clever folks, some far smarter than you or I, have been attempting to solve this exact problem for the past 20 years. If it was so simple, someone would have already done it." He paused, then added, "Besides, the Navy has strict standards and specifications. We can't just change procedures based on a new idea from a welder without getting the proper approvals from the Bureau of Ships in Washington. You understand the bureaucracy." Despite the discouragement, Nelson clung to the belief that his inventive approach could ultimately transform naval construction, should he be given the opportunity to demonstrate its practicality and gain the necessary approvals from the bureaucratic machinery. Yet, he knew the process would be arduous, requiring persistence and patience in the face of rigid standards and in the midst of intensive development efforts. Substantial research and development phases are crucial before implementing any new technology. However, this process often spans several years, requiring extensive prototype testing and validation. Nelson urgently needed to move beyond these lengthy stages. It was a matter of survival and strategic necessity. "We do not have years," he firmly protested, emphasizing the immediacy of their situation. "We need submarines now, not in some distant future." Hartwell, though, brushed off his concerns with a nonchalant shrug, indicating he was not persuaded. "That is not my problem, Mr. Nelson," he stated dismissively. "My responsibility is limited to building ships according to the approved specifications set forth by the authorities." Nelson understood the limitations imposed by bureaucratic procedures and standardized protocols, but he also recognized that such inflexibility was instrumental in causing delays and inefficiencies. However, Nelson believed that rigid adherence to protocols should never impede innovation, especially when the potential gains were tremendous. His frustration grew as he realized that his suggestions could significantly reduce the time and effort spent on manufacturing each submarine, savings amounting to thousands of hours per vessel. Yet, his ideas had been dismissed almost without consideration. The primary reason wasn't the flaws in his concept, nor doubts about its effectiveness, but rather his position as merely a welder. His role did not grant him authority to influence major procedural changes. The thought of endless paperwork and the need for approvals loomed large, processes that stifled practical innovation and delayed progress. Feeling both disillusioned and determined, Nelson made one final effort. He composed a meticulously written, formal letter addressed to the shipyard commander, Captain Thomas Withers, aiming to present his idea professionally and persuasively. In this letter, he clearly outlined the inefficiencies plaguing current procedures, detailed his proposal for a revolutionary stud welding technique, and estimated the significant time and cost savings it could deliver. He submitted his suggestion through the proper channels, adhering strictly to the official procedure for worker proposals, hoping that this approach might garner more serious consideration. 3 weeks later, Nelson received a reply, a standard, form letter response thanking him for his interest in improving shipyard efficiency. It explained politely that all technical proposals were reviewed and evaluated by the Bureau of Ships Engineering Review Board. A notation indicated that his suggestion had been forwarded for consideration, but it also included a sobering fact. The typical review process could take from 18 to 24 months. As Nelson read this, a sense of dread and frustration settled over him. By the time any decision might be made, the war could already be over, or perhaps lost altogether. In a state of resignation, he crumpled the letter and threw it into the waste bin, feeling that hope was slipping away. Yet, that evening, a profound decision took shape in his mind, one that would ultimately change his life forever and leave a mark on naval history itself. If the Navy refused to listen to his ideas, then he would take matters into his own hands. He resolved to build the device himself, to prove that his concept was viable and effective. Once proven, the authorities would have no choice but to pay attention. With unwavering resolve, Nelson cleared a small space in his garage behind his modest cottage in Vallejo, preparing for the journey ahead. His wife, Emma, watched him with concern, sensing the extraordinary level of his determination. "Ted, you're going to get yourself fired," she warned, aware of the risks involved in defying the established system. "You're supposed to be working on Navy projects, not your own inventions." Nelson reassured her, "This will help the Navy," he said confidently. "They just don't realize it yet." Over the ensuing weeks, every spare moment he had, after work in the evenings and on weekends, was dedicated to constructing his first prototype of the stud welding gun. His efforts were fueled by a mix of hope and stubborn resolve. The initial design was simple yet functional. It consisted of a pistol grip handle, a spring-loaded plunger to hold and press the weld stud, an electrical trigger connected to a powerful welding supply, and a quick-release mechanism for loading new studs efficiently. However, the most innovative component of his design was the flux cap. Nelson experimented tirelessly with various ceramic materials, different flux compositions, and multiple cap designs, refining his ideas through numerous tests. After dozens of trials, he finally succeeded in developing a flux cap that held the flux securely, initiated the arc properly, and was inexpensive to produce in large quantities. By May of the year 1941, he had managed to create a fully functioning prototype that met all his criteria. He then rigorously tested the device on scrap steel, attempting it in every conceivable orientation: horizontal, vertical, overhead, and various angled positions. These experiments confirmed that his prototype was capable of delivering consistent, reliable welds regardless of position, demonstrating its practical viability and robustness. In moments of crisis, innovation can often serve as the most vital solution. Such was the case with Nelson, whose welding technology had been progressing quietly, yet rapidly, before the winds of war truly swept through the nation. His invention, an efficient and quick method of welding studs, was initially tested with ease. Each weld took less than a second to complete. Remarkably, the strength of these welds surpassed that achieved through traditional through-bolting techniques, and crucially, they required no access beneath the surface being worked on. Nelson had brought his prototype to work one day, quickly demonstrated its capabilities during a lunch break to multiple fellow welders, and the reaction was unmistakably positive. They were captivated and buzzing with excitement at the rapidity and robustness of his device. One worker commented that this invention was going to revolutionize their workflow, drastically reducing the time spent on assembly tasks. Another suggested that he should demonstrate it to Morrison, perhaps someone in a managerial position, who might see its potential. Nelson, however, shook his head with a note of disappointment, revealing that he had already shown Morrison during previous presentations. Morrison had dismissed the device outright, showing no interest or openness to its revolutionary concept. Frustrated but undeterred, one of Nelson's colleagues even went further, advising him to consider selling his welding gun to shipyards across the country, asserting that doing so could make Nelson extraordinarily wealthy. This proposition was only then beginning to take root in Nelson's thoughts. He recognized that he was a skilled welder but not a businessman. He lacked the financial resources, manufacturing facilities, and business expertise required to commercialize his invention on his own. Nevertheless, the more he contemplated this possibility, the more sense it made to him. If the Navy, with its enormous wartime needs, wasn't willing to adopt his innovation, perhaps private shipyards, many of which were struggling, would be interested. Indeed, during this period, shipyards along the West Coast were experiencing severe labor shortages and relentless production pressures. The Kaiser shipyards in Richmond were actively hiring, and the Bethlehem Steel Shipyard in San Francisco was expanding rapidly. Numerous shipyards from Northern to Southern California were all desperate for efficient means to speed up their work. The country's shipbuilding effort was quickly transforming into a national priority, a patriotic effort to produce ships as quickly and as efficiently as possible to support the war effort. On June 20, 1941, just months before the United States officially entered the conflict, Ted Nelson took a decisive step backward from his previous job that contributed to national defense. He submitted his resignation from Mare Island Naval Shipyard. His supervisor attempted to dissuade him, emphasizing Nelson's remarkable skill as a welder and cautioning him against throwing away a stable career for a new, unproven invention. Yet, Nelson was resolute. His mind was already set on building a company dedicated to his welding guns, and he boldly told Morrison that he intended to pursue this new venture, warning that he hoped Morrison would remember their conversation once his plans materialized. With only $11 remaining in his pocket and an arsenal of tools stored in his garage, Nelson departed the shipyard with unwavering conviction that his invention could succeed. He registered his new company, the Nelson Specialty Welding Equipment Corporation, on July 1, 1941, and immediately sought funding. To finance his enterprise, he secured a loan of $95,000 from the Reconstruction Finance Corporation, a government agency established during the Great Depression to support small businesses and stimulate economic recovery. This was a significant step for a fledgling startup. With this capital, Nelson rented a modest workshop in Vallejo and set about manufacturing his stud welding guns. The initial months were undeniably challenging. He faced the formidable obstacle of having no existing customer base, no reputation, and no established distribution network. Nonetheless, Nelson began knocking on doors, contacting local machine shops and small fabrication companies, demonstrating his device, and explaining how it could dramatically reduce their welding time. He encountered skepticism, which was expected, but a few clients agreed to try out demo units. Gradually, word about his innovative welding gun spread, and although progress was slow, it was steady. By September of the same year, Nelson had managed to sell 18 welding guns, alongside several thousand flux-capped studs, marking the first tangible signs of commercial viability. Then, on the historic date of December 7, 1941, everything changed forever. The attack on Pearl Harbor by Japanese forces struck the United States, igniting a total war effort. The assault resulted in the destruction or severe damage of 8 battleships, 3 cruisers, 3 destroyers, along with nearly 288 aircraft. The country mourned the loss of approximately 2,430 Americans and, more critically, found itself abruptly thrust into conflict. Suddenly, the importance of shipbuilding was no longer merely strategic but became a matter of national survival. The urgency to produce ships at an unprecedented rate transformed shipyards into bustling centers of frantic, all-hands yards across the country had been suddenly compelled to operate on triple shifts, working around the clock to keep pace with the relentless demand for ships. Each facility encountered the same pressing challenge. How can they construct ships quickly enough to meet wartime needs? Traditional shipbuilding methods, once considered efficient, now proved sluggish, heavily reliant on labor-intensive processes, and ultimately too wasteful of precious time. It was amid this intense pressure that Ted Nelson's phone began to ring unexpectedly. Engineers and procurement officers from various shipyards, who had previously dismissed his technological innovations weeks earlier as unnecessary or unproven, suddenly found themselves eager to place substantial orders for his welding equipment. Within a short span, the Kaiser shipyards ordered 50 of Nelson's advanced welding guns along with 10,000 studs. Bethlehem Steel, another major partner, followed swiftly with an order for 40 guns. Even the Mare Island Naval Shipyard, a facility that had turned down Nelson's ideas just a few months prior, reversed course and placed an order for 60 guns and 20,000 studs. Narratives reveal that Morrison, Ted Nelson's former supervisor, was the one who processed these requisitions. However, there was neither an apology nor acknowledgement of Nelson's earlier foresight. Instead, the orders arrived as cold, official requests with urgent expectations for quick delivery. By the early months of the year 1942, less than a month after the attack on Pearl Harbor, Nelson's small workshop was overwhelmed by the wave of new orders. He found himself struggling to keep pace, as demand surged beyond what he could produce in his existing setup. He recognized he needed much more: a proper factory space, additional skilled workers, and superior manufacturing equipment. Consequently, he leased a larger facility located in San Leandro, just a few miles south of Oakland. The new building sat isolated amidst a sprawling cornfield, unassuming and modest in appearance, yet it offered ample space, robust power supplies, and potential for future expansion. By March of 1942, Nelson had employed just 20 workers in his new facility. This number doubled by June and tripled again by September, reaching a total of 150 employees. The factory shifted into continuous operation, functioning around the clock, 7 days a week. The assembly line was humming with activity. Welding guns were turning out at a weekly rate of around 30 units, while the production of studs escalated into the thousands daily. As a result, every significant shipyard along the West Coast found Nelson's stud welding equipment indispensable for ship construction. The feedback from these yards was overwhelmingly positive. Reports detailed transformations that previously would have taken 6 days and a dozen workers now completed in a single day with just 3. The notable advantages extended beyond speed alone. Welded joints proved to be inherently stronger than conventional bolted connections, which meant the wooden deck planks, used in shipbuilding, could now be replaced or repaired more effortlessly. This innovation significantly sped up maintenance procedures. For example, at the Mare Island Naval Shipyard, the process of assembling submarines experienced unprecedented acceleration. Between 1941 and 1945, the yard completed 17 submarines, with the time taken for each vessel decreasing markedly as Nelson's techniques became more widely adopted. Nelson's stud welding wasn't merely a one-trick pony. It rapidly became a multifaceted solution in shipbuilding and beyond. By mid-1942, its applications broadened to include a wide array of tasks. Engineers used it to fasten pipe hangers, cable supports, equipment mounts, and bulkhead attachments, virtually anywhere a steel fastener was required. With the Navy Bureau of Ships initially dismissing Nelson's ideas, the tide turned as they began to study and analyze his process in depth. The engineering teams scrutinized weld strength, long-term durability, and failure modes, eventually confirming what Nelson had known all along. His welds were not only faster but also superior in strength and reliability. On November 19, 1942, just 11 months after earning a modest $11 a day wage, the significance of Nelson's innovation became undeniable. His impact was so profound that it changed the course of wartime shipbuilding, turning his small workshop into a crucial contributor to the Allied efforts. The story of stud welding exemplifies how a single inventive insight, when realized through determination and strategic scaling, can dramatically reshape an entire industry. In the midst of his welding endeavors, Ted Nelson found himself unexpectedly visited by a delegation of Navy officers, who arrived at his San Leandro manufacturing plant without warning. The group consisted of 5 distinguished gentlemen dressed impeccably in formal uniform attire, clearly representatives of the naval forces. Leading the visitors was Captain Harrison, an official from the Bureau of Ships, who took it upon himself to speak on behalf of the delegation. With a composed but authoritative tone, Captain Harrison began, "Mr. Nelson, we've come here today to inform you that the Navy has completed its thorough evaluation of your stud welding process." He paused briefly before continuing, "Our assessment indicates that your groundbreaking invention has, over the past 10 months, saved the United States Navy an estimated 5 million man-hours in the construction of both submarines and surface ships. This significant reduction in labor time is poised to grow considerably as additional shipyards adopt this technology." He then Rajatected to contemplate before going on behalf of the Secretary of the Navy and the American government, I am authorized to present you with a citation acknowledging your exceptional contribution to our war effort. The news struck Nelson utterly unprepared. He was visibly taken aback. Years prior, the Navy had dismissed his innovative ideas and tried to discard his proposals. They had repeatedly ignored his efforts, forcing him to leave his previous job and gamble everything to develop his technology independently. Now, after all that struggle and perseverance, they were bestowing upon him an official recognition. Captain Harrison, understanding the conflicted look on Nelson's face, offered some clarification. "I believe you remember submitting a proposal to Mayor Island early in 1941, Mr. Nelson," he said kindly. "I have reviewed those files, and it's clear that your proposal back then was not given the proper consideration it deserved at the time. That was an oversight on the part of the Navy, and I apologize for that." He paused, then added thoughtfully, "However, your decision to carry out the development independently has resulted in a much faster deployment than could have been achieved through the normal procurement procedures. Sometimes, when the goal is to serve your country best, it's necessary to go beyond official channels and focus solely on solving the problem." When Nelson accepted the citation, he experienced a complex mix of emotions. Pride in his achievement and a sense of vindication for his relentless efforts contrasted sharply with lingering frustration toward the bureaucratic obstacles that had nearly prevented this innovation from coming to fruition. The prevailing conflict between perseverance and institutional rigidity lingered in his mind, even as the war raged on. As the conflict persisted and the demands for production skyrocketed, Nelson's enterprise continued to expand. In March of 1943, his company, Nelson Specialty Welding Equipment Corporation, opened a second manufacturing plant on the East Coast, situated in Camden, New Jersey. This new facility was tasked with supplying shipyards in New York, Philadelphia, Norfolk, and Charleston, ensuring that his welding technology supported a vast network of wartime construction. By the middle of that same year, Nelson's company employed over 400 workers and accounted for an annual revenue approaching $4 million, a significant figure at the time. Despite his expanding enterprise, Ted Nelson maintained a work ethic characterized by relentless dedication. He was often found toiling in the factory for up to 16 hours each day, dressed in his familiar shop workers' tan pants and shirts. His modest salary of around $1,000 each month was mostly reinvested into his business, funds put toward expanding facilities, acquiring new equipment, and paying off loans necessary for continuous growth. What Nelson achieved, however, transcended financial metrics. His contribution to the war effort was profound and far-reaching. While the earlier estimate of saving 5 million man-hours by late 1942 was impressive, it was merely a starting point. As the war escalated and stud welding became integrated into the standard procedures of naval construction, these time savings grew at an exponential rate. By 1943, stud welding was being employed not only on submarines but also extensively on aircraft carriers, battleships, cruisers, destroyers, and myriad smaller vessels. For example, the aircraft carriers of the Essex class, manufactured by Newport News Shipbuilding and other shipyards, relied heavily on Nelson's welding technology for attaching flight decks and interior fittings. The impact of his innovation was evident across the vast array of naval vessels, transforming the pace and efficiency of wartime shipbuilding and contributing profoundly to the overall success of the Allied naval efforts during this critical period. During World War II, the United States' vast naval and merchant fleet construction programs demanded immense amounts of specialized assembly techniques. One particularly significant innovation was the use of stud welding, which played a crucial role in speeding up the manufacturing processes across different types of vessels, from submarines to cargo ships. It was estimated that to meet wartime production goals, approximately 20,000 studs were needed for various assembly tasks. Throughout the conflict, the Navy engaged in the construction of an impressive fleet of aircraft carriers, specifically 24 Essex-class carriers, which served as a backbone of naval power during the war. The technological advances in fastening methods, notably stud welding, finding widespread application across different ship classes, contributed to increasing both the strength and the speed of assembly. For example, on the battleship front, the formidable Iowa class utilized stud welding extensively for attaching deck planking, installing vital equipment mounts, and securing armor panels, thus ensuring rapid yet sturdy construction. The Baltimore-class heavy cruisers exemplified the broad implementation of stud welding technology, incorporating it at virtually every stage of construction, from hull assembly to internal fittings. What was true for large capital ships was even more dramatically evident in the realm of submarine construction. At Mayer Island Naval Shipyard, famous as the place where Nelson, a pioneering engineer whose ideas about welding had initially been turned down, once worked, the efficiency of submarine production notably surged. Over time, this yard emerged as one of the most prolific and efficient submarine builders in history, completing a total of 17 submarines during the war, with each successive vessel benefiting from steadily shorter construction times. In a particularly remarkable display of industrial achievement, Port South Naval Shipyard in New Hampshire became a leader in submarine output. Between July of 1940 and July of 1945, this yard successfully built 79 submarines. The success of Port South was no accident. It was rooted in numerous innovations, at the core of which was stud welding, a technology that proved indispensable not only for attaching deck components but also extensively inside the submarine's hulls and internal spaces. The comprehensive adoption of Nelson's stud welding system throughout the shipyard transformed the construction process, making it both faster and more reliable, as evidenced by the yard's impressive output numbers. A landmark moment occurred on January 27, 1944, when Port South managed to launch an unprecedented 4 submarines simultaneously. These included the Redfish, Ronquil, Razorback, and the Scabbardfish. Launching 4 vessels in a single day was, and remains, a unique feat in naval history. The yard's most productive year, 1944, saw the completion of 32 submarines, averaging approximately 1 every 11 days. The submarines of the Baltimore class, which accounted for the majority of wartime submarine production, typically took about 12 months from keel laying to commissioning at Portsmouth. This was several months faster than comparable yards building similar classes, highlighting the efficiencies gained through technological innovations like stud welding. Beyond Portsmouth, other shipbuilders contributed significantly to submarine production during the war. The Electric Boat Company in Groton, Connecticut, built an impressive 74 submarines. Meanwhile, Mantarock Shipbuilding in Wisconsin, despite being inland and situated on the Great Lakes, hundreds of miles from the Atlantic or Pacific, successfully built 28 submarines, which were then floated down the Mississippi River to reach the Gulf of Mexico for delivery and deployment. When considering all shipyards involved, the United States managed to produce a total of 203 submarines during the course of the Second World War. Each submarine demanded thousands of stud-welded attachments, small yet crucial elements that reinforced entire sections of the craft. The significance of stud welding extended far beyond just warships. It was essential to the production of surface vessels and merchant ships as well. The Liberty Ship Program, which was administered by the Maritime Commission and primarily executed at Kaiser shipyards, led to the enormous construction of a total of 2,710 cargo ships. These vessels represented another massive deployment of stud welding technology, each ship requiring between 5,000 and 8,000 stud-welded attachments to secure deck planks, cargo handling gear, defensive weapon mounts, and numerous other fittings essential for seaworthiness and operational functionality. The Victory ships, designed to be faster and more robust, were built using similar standards and fabrication methods, including the extensive use of stud welding, thus maintaining the same high-volume, rapid production pace. The scale of this wartime manufacturing effort was unprecedented in human history. During the peak year of Liberty ship construction in 1943, American shipyards were launching 3 new ships each day. This translated into approximately 75 ships every month, or around 900 ships annually. Such relentless, massive production underscored the extraordinary industrial capacity and innovative techniques utilized during the war, which collectively enabled the United States to supply its military and allies with a vast and diverse fleet of vessels capable of supporting global wartime operations. The advancements in shipbuilding during that pivotal era were fundamentally driven by a series of groundbreaking innovations that transformed traditional construction processes into a streamlined, highly efficient system. These innovations encompassed the adoption of pioneering manufacturing techniques like prefabrication and modular assembly, the employment of specialized workers trained specifically for these new methods, the utilization of dedicated tools designed for rapid deployment, and the development of faster, more effective attachment methods. Among these technological breakthroughs, stud welding emerged as a crucial component of a broader movement aimed at revolutionizing naval construction. Although it was just one element within a comprehensive transformation, its significance was undoubtedly profound. The introduction of stud welding eliminated the reliance on cumbersome scaffolding frameworks, which historically consumed vast amounts of time and labor, thereby freeing up construction crews to focus on other vital tasks and accelerating the overall building process. The ability to install structural components at a much faster pace substantially reduced the time required for assembly. Furthermore, the durable and reliable welds produced through this technique ensured that even the hastily assembled ships met the rigorous standards of strength and resilience necessary to withstand the ferocious North Atlantic storms and potential enemy attacks. By the spring of the year 1943, the United States Navy had publicly acknowledged Nelson's pivotal contribution to this technological shift. His work had become a symbol of innovation that played a vital role in wartime production. On the 11th of May in 1943, the Secretary of the Navy formally awarded the Nelson Specialty Welding Equipment Corporation the prestigious Army-Navy E Award for Excellence in Production. This accolade was established in July of 1942 to honor companies that demonstrated exceptional performance in the manufacturing of war materials. The criteria for this recognition prioritized not only the quality and durability of the outputs but also the quantity produced within given timeframes. Historically, only about a handful of companies, roughly 5%, engaged in wartime manufacturing had been accorded this honor, marking it as a symbol of elite achievement. Receiving the award entailed an official presentation that included a ceremonial pennant bestowed upon the factory and individual pins awarded to all employees who had participated in meeting the intense production demands. The award ceremony took place at Nelson's plant in San Leandro, with the occasion marked by full military honors that underscored its importance. Attendees included representatives from the Navy, Army officials, and local dignitaries, all gathered to recognize the extraordinary efforts of the factory workers. These workers, Nelson's dedicated employees, had endured grueling hours and challenging conditions, often working into the late hours to fulfill the relentless wartime production quotas. Their pride was evident as they received their pins, a tangible acknowledgement of their invaluable contribution. Ted Nelson, standing before his workforce dressed in his customary work attire, accepted the pennant with a sense of humility and addressed the assembled crowd. He emphasized that their efforts were not driven by the pursuit of awards or personal recognition but rather by a steadfast commitment to their country's needs. In his words, every stud they produced and every weapon they helped build played a part in ensuring the safe return of sailors and soldiers from the battlefields. The true reward, he proclaimed, was knowing that their work helped bring servicemen home safely. Yet, the Navy's recognition of Nelson's innovation did not end there. The organization had established a system whereby plants demonstrating sustained outstanding performance, maintaining the high standards for at least 6 months after receiving the initial E Award, could earn additional distinctions in the form of stars that were added to their pennants. Nelson's plant achieved its first of these stars in November of 1943 and a second one in May of 1944, signifying enduring excellence over a prolonged period. By the conclusion of the war, the Nelson Specialty Welding Equipment Corporation had distinguished itself further by earning not just one, but 2 E Awards adorned with stars, an honor attained by only a select few companies engaged in wartime manufacturing. The official citations highlighted the fact that their innovations and dedication had collectively contributed to an estimated saving of 50 million man-hours in naval construction alone. To grasp the magnitude of this achievement, consider that 50 million hours of work span roughly 5,700 years. If one individual were to work tirelessly, 8 hours every day, it would take more than 19,000 years to accumulate such an amount of labor. This monumental time saving stemmed from a single, ingenious innovation, a spring-loaded welding gun complemented by a ceramic flux cap, that drastically enhanced the speed of assembly. The repercussions of this technological leap were profound and far-reaching. Ships could be launched into the water at an unprecedented rate, enabling the rapid deployment of submarines to hunt down Japanese convoys, destroyers to escort vital supply chains across treacherous waters, and aircraft carriers to launch strikes that could shift the tide of naval battles. More landing ships could bring troops to hostile beaches faster, facilitating amphibious assaults crucial for offensive operations. Each day shaved off the build time translated into increased combat power, more supplies delivered to the front lines, and countless lives potentially saved, a strategic advantage that proved essential in turning the tide of the conflict. The significance of that act was truly incalculable, yet its importance extended far beyond mere technical achievement. Nelson's innovative approach brought about an unintended yet immensely beneficial consequence. It lowered the barrier to entry for skilled labor in the wartime shipbuilding industry. Unlike traditional methods such as bolt fastening or conventional welding, the stud welding process was remarkably simpler to learn and master. This meant that, with only minimal training, new workers, regardless of their prior experience, could quickly and confidently operate stud welding equipment, performing their tasks both safely and effectively. This development proved to be particularly vital as the war advanced, and the demand for rapid production intensified amidst mounting labor shortages. An extraordinary influx of women into the shipyards marked a new chapter in American wartime industry. These women, symbolized by the renowned Rosie the Riveter, became emblematic figures of the female workforce, yet alongside them were women who specialized in welding, earning recognition for their skilled craftsmanship. These female workers operated stud welding guns, installed planking on the decks, and mounted various pieces of equipment, many of them eventually mastering the process to the point of becoming highly skilled technicians. During the peak of wartime activity, the Mayer Island Naval Shipyard employed almost 50,000 workers, an impressive number including around 9,000 women. Similarly, the Kaiser shipyards, which played a crucial role in the shipbuilding effort, employed hundreds of thousands of workers, with women constituting nearly 30% of the total workforce. These women needed tools and procedures that could be taught swiftly, implemented safely, and relied upon to maintain continuous production. The simplicity and effectiveness of stud welding proved to be an ideal solution, perfectly matching these requirements. By the year 1944, the momentum of the war had shifted decisively in favor of the Allied powers. American industrial productivity surged past that of the Axis nations, producing an astonishing volume of ships, aircraft, tanks, and artillery, more than Germany and Japan combined. President Franklin D. Roosevelt famously called this effort the arsenal of democracy, emphasizing its central role in the victory. The United States operated at full capacity, churning out vast quantities of military equipment to meet the demands of a war unlike any other. In this grand industrial enterprise, Ted Nelson's stud welding guns contributed, a seemingly small component of the broader machinery that supported the war effort. Yet, in times of conflict, the smallest parts can have profound impacts. When it comes to wartime efficiency, the measure of success isn't just in the number of ships or aircraft produced but in lives saved and battles won. Faster ship construction meant deploying a larger navy more swiftly, which translated directly into strategic advantages. A greater naval presence led to more Japanese shipping vessels sunk, islands captured, and pressure applied to the enemy's maritime logistics. The effectiveness of this approach was clearly demonstrated in the Pacific submarine campaign. American submarines succeeded in sinking over 1,000 Japanese merchant ships, totaling approximately 5 million tons of cargo, an amount that severely hampered Japanese supply lines. This destructive pattern extended to military vessels. They sank 1 aircraft carrier, 8 battleships, along with numerous cruisers and destroyers. Such results were only achievable because America built submarines at a faster rate than Japan could lose them, ensuring continued pressure on the enemy fleet. At the start of the conflict, Japan's submarine fleet was larger than that of the United States. However, during the course of the war, Japan constructed only a total of 126 submarines, whereas the United States increased its fleet to exceed 200 and, by the war's end, approached 203 submarines. Every month of accelerated production proved crucial. Each submarine reaching operational status meant another week of relentless patrols hunting enemy shipping, a vital advantage in the broader naval war. This pattern of rapid construction and deployment also defined the story of the Essex-class aircraft carriers, which eventually formed the backbone of America's carrier fleet. In December of 1941, the U.S. Navy possessed only 7 such carriers. By August of 1945, the fleet had expanded dramatically to encompass 99 carriers of various types. The Essex class played a particularly pivotal role, with 24 ships completed during the war, each capable of carrying up to 90 aircraft. These fast carriers became the centerpiece of naval operations in the Pacific from mid-1943 onward, facilitating a new level of dominance. The carriers launched relentless air strikes against Japanese positions, offered crucial air cover during amphibious assaults, and engaged Japanese naval forces in decisive and devastating battles. The Battle of the Philippine Sea in June of 1944 stands out as a striking example, where American carrier-based aircraft destroyed over 600 Japanese planes, an event which pilots collectively referred to as the Great Mariana Turkey Shoot. This battle effectively shattered Japanese naval air strength and marked a turning point in the Allied Pacific campaign, illustrating the tremendous power and strategic value of the expanded U.S. Navy supported by rapid manufacturing breakthroughs such as Nelson's stud welding technology. The victory in this context hinged entirely on the United States possessing a larger fleet of aircraft carriers positioned wisely in key locations at just the right moments. The rapid pace at which American shipyards could construct these vessels directly influenced how swiftly they could be deployed into battle. A stark illustration of this was the D-Day invasion of Normandy, which took place on June 6, 1944. It required an astonishing 7,000 ships and landing craft to carry out the assault. This massive amphibious operation, which stands as the largest in the history of warfare, could only be feasible because American and British shipyards had worked tirelessly, producing landing craft in the thousands. These vessels, though relatively simple in design, flat-bottomed boats built to roll up onto beaches and unload troops, equipment, and supplies, still demanded fast construction methods and extremely reliable fittings to ensure they could perform under hectic and stressful conditions. One of the key technological innovations that proved particularly well suited for the rapid construction of these landing crafts was stud welding. This technique allowed for the quick and secure attachment of cargo ramps, davit mounts, deck fittings, and other essential components, significantly reducing assembly time. A notable example was the application of Nelson's deck attachment technology, originally developed for submarines, which found extensive use across the entire fleet of landing crafts, ensuring speed and reliability in their manufacturing. However, by May of 1945, marked as V-Day, the focus of the war effort shifted fully toward the vast theater of the Pacific. Military planners prepared for the imminent invasion of Japan, codenamed Operation Downfall, which was scheduled to commence in November of that same year. The scale of this planned assault was unprecedented, requiring more ships, more landing craft, and an enormous logistical support system far exceeding anything seen in previous campaigns. Shipyards around the country prepared tirelessly to meet this anticipated demand, scaling up production even further. Then, a sudden and dramatic turn of events occurred. On August 6 and 9, 1945, atomic bombs were dropped on Hiroshima and Nagasaki, causing devastation and ultimately compelling Japan to surrender unconditionally. The official surrender came on August 15, bringing an end to years of brutal conflict, marking the conclusion of World War II. With the end of the war, the United States' vast military production apparatus gradually began to wind down. Contracts that had fueled wartime manufacturing were canceled en masse, and millions of workers who had once powered the factories found themselves being laid off. Many shipyards either closed entirely or reoriented to peacetime production, transforming from war-focused to civilian-oriented industries. Among the companies affected was the Nelson Specialty Welding Equipment Corporation, which had seen its workforce swell to over 400 during the height of wartime manufacturing. Overnight, military orders vanished, leaving their future uncertain. Yet, Ted Nelson, mindful of the impending peace, had already been exploring potential civilian applications for stud welding, learning early on that this technology was not confined merely to shipbuilding. Instead, it held significant promise for any industry involved in steel fabrication, powerful enough to revolutionize how steel components were attached in constructing bridges, buildings, tanks, pressure vessels, and even automotive parts. Recognizing these broader opportunities, Nelson shifted his company's focus toward the commercial sector, actively marketing his stud welding systems to construction firms, steel fabricators, and industrial manufacturers. The post-war reconstruction boom soon provided a fertile ground for this new direction. America embarked on vast projects of highway construction, bridge building, skyscraper development, and the expansion of suburban areas, each demanding extensive steel fabrication and quick, dependable attachment methods. By 1948, Nelson's company had successfully transitioned from wartime to peacetime production, albeit at a smaller scale than before, but with a stable foundation for growth. The firm continued to innovate, developing new designs for stud connectors, enhancing welding technology, and creating specialized solutions for various industries. In 1950, Nelson ultimately opted to sell his company to TRW, a major industrial conglomerate. This transaction ensured his financial security and allowed him to retire from day-to-day management, but the Nelson legacy persisted, as the Nelson name remained attached to the products, symbolizing quality and innovation. TRW continued marketing Nelson's stud welding equipment, preserving the brand recognition Ted Nelson had painstakingly built over the years. As decades passed, the company experienced various changes in ownership and management, reflecting the dynamic nature of technological and industrial evolution, but the foundation laid during the war years and the post-war transformation remained a testament to Nelson's foresight and adaptability. Throughout numerous decades, the Nelson name has persisted despite an ever-changing corporate landscape. Originally developing innovations in the field of welding, the company underwent several ownership transitions before settling into its current embodiment. In the year 2000, the firm known as TRW transferred its assets to a company called Farsantech Incorporated, in a move that marked a significant turning point for Nelson's legacy. Later, in 2007, Farsantech itself was acquired by Doncasters Group Limited, a broader conglomerate seeking to expand its portfolio. The following year, in 2018, Stanley Black & Decker, a well-known global leader in tools and industrial solutions, purchased what remained of the company's industrial division. Amid all these corporate reorganizations, the brand name Nelson endured, retaining its recognition and reputation. Today, the organization is known as Stanley Engineered Fastening, and it continues to design, produce, and distribute Nelson's pioneering stud welding products across the world. The technology that Ted Nelson first developed, initially in the basement of his home garage in Vallejo, still forms the core of modern stud welding operations, underscoring the durability and longevity of his innovations. Contemporary advancements have certainly refined and expanded upon Nelson's original concepts. Modern stud welding employs sophisticated inverter power supplies, which enable highly precise control over the electric arc essential for welding. Manufacturing plants leverage automated systems to handle high quantities of studs with remarkable efficiency, while robotic welding arms can rapidly attach studs in large-scale automotive assembly lines. Despite these technological enhancements, the fundamental principles remain unchanged. A stud, a flux cap, a spring-loaded gun, and an electrical arc working together to produce a weld in approximately 1 second per individual fastener. One of the most compelling features of this process is the elimination of scaffolding or extensive setup that was once necessary. The adaptability of stud welding has led to its application across an array of industries far beyond its initial maritime origins. Today, construction workers use this technology extensively for attaching metal decking to steel framework in the construction of skyscrapers, providing a quick and reliable fastening method. Bridge engineers harness it to secure guardrail posts and place lighting fixtures along critical infrastructure. In the realm of nuclear energy, the process is employed for installing cable trays and mounting various heavy equipment securely. Automotive industry giants rely on stud welding throughout entire vehicle bodies to establish grounding points and affix trim pieces, streamlining assembly and improving durability. The technological solution Ted Nelson devised to address problems during naval shipbuilding has proven to be invaluable across virtually all sectors that work with steel. Yet, perhaps one of the most poignant legacies of Nelson's invention lies in the context of historic preservation. Today, the battleship Texas, which is one of merely 7 remaining vessels that served in both World War I and World War II, is undergoing an extensive restoration at a specialized dry dock facility. The vessel needs comprehensive repairs, replacing corroded hull plates and fixing aging fittings, and the restoration crew found that modern Nelson stud welding equipment is ideally suited for this purpose. Remarkably, they can attach new steel plates to the old structure using the very same technology that Ted Nelson pioneered approximately 8 decades ago. Similarly, the World War II submarine USS Pompanito, now preserved as a museum in San Francisco, continues to rely on Nelson's stud welding technique for its ongoing maintenance activities. The ship attracts over 100,000 visitors annually, eager to explore a piece of history. Ensuring the vessel remains safe and operational requires continual attention, which is made possible by the efficiency of Nelson's invention. The equipment allows volunteer restoration teams to perform welding tasks effectively, often without the need for highly specialized, certified welders to be present at each step. Ted Nelson lived to witness the profound reach of his contributions, seeing his original idea evolve into an industry-wide standard that transformed construction, manufacturing, and preservation alike. His invention not only became a staple in shipbuilding but also saw adoption across multiple industries across the globe. As his name became almost synonymous with the welding process he created, Nelson continued to see his work impact daily life in ways he had never imagined when scribbling his concepts into a notebook on a quiet day in 1941. He passed away in 1994, comfortably reaching the age of 89. By that time, he had witnessed significant world events, shedding the Cold War's shadow and observing dramatic changes within the global landscape that his generation had fought and strived to preserve. The impressive statistics attached to his achievements, such as saving 50 million man-hours, earning 2 Army-Navy awards, aiding in construction of thousands of ships at a faster pace, and producing billions of studs, are only partial reflections of the true impact. Numbers do not fully convey the profound influence Nelson's innovation has wielded, bringing safety, efficiency, and progress to industries, and leaving a lasting mark that continues to inspire today. The silent, most enduring honors of his effort. His ingenuity exemplified a core principle of innovation. Success often comes not from seeking applause but from steadfastly pursuing a better way, regardless of skepticism or bureaucratic resistance. Throughout history, countless visionaries faced similar dismissals. Wilbur and Orville Wright, for instance, encountered skepticism from seasoned experts who insisted that powered flight was an unattainable dream. Many ridiculed Henry Ford's bold idea of mass-producing automobiles, dismissing it as impractical or too radical for the existing market. Chester Carlson, the inventor of xerography, spent years pitch after pitch trying to persuade others of his revolutionary printing process, only to find rejection after rejection before finally securing a buyer. What distinguished Ted Nelson from many others was his unwavering refusal to accept defeat. He didn't engage in fruitless arguments with officials skeptical of his ideas. Instead, he chose a different path altogether. He made a decisive leap, leaving his job, risking his modest savings, and demonstrated that his welding technique could deliver tangible results. Once he proved his method's effectiveness, the market itself recognized its value, forcing broader acceptance and implementation. This relentless pursuit typifies the spirit of American innovation, one of bold action without waiting for formal approval or bureaucratic permissions. It involves identifying critical problems, creatively developing solutions, and then summoning the courage to see those solutions through, even when faced with institutional resistance or skeptical authorities. Nelson's workplace, the Mayer Island Naval Shipyard, where his idea was initially dismissed, serving for over a century before closing in 1996, stands as a testament to this resilience. Throughout its existence, the shipyard produced and repaired an extraordinary number of vessels, 512 ships, including the final nuclear submarine constructed in California, the USS Drum, launched in 1970. It earned recognition as a California Historical Landmark in 1960 and was designated a National Historic Landmark District in 1975. Today, the site has been transformed into a dynamic mix of commercial and residential development. Some of the historic structures remain, from the charming chapel to old dry docks and industrial buildings. Walking through these preserved relics, visitors can vividly imagine the bustle and urgency that filled the yard during the wartime years, when tens of thousands of workers toiled tirelessly around the clock to construct and repair submarines under immense pressure. One notable remnant is Building 46, the old pipe shop operational until 1984, which is now home to a small museum. This exhibit showcases tools, photographs, and artifacts that serve as tangible links to the shipyard's legacy. Curiously absent, however, is any specific tribute to Ted Nelson. There is no monument celebrating the welder who did 50 million man-hours of labor, nor any extensive display of his work. His story remains largely concealed within the circles of welding professionals and maritime history buffs, seldom recognized by mainstream memory. Yet, perhaps Nelson would not have minded such obscurity. His quest was never about fame or quick recognition. His primary motivation was addressing a pressing challenge, finding a better way to weld, a way that could save time, preserve lives, and make a meaningful impact on his country's efforts during wartime. To him, these tangible results, the improved efficiency, the lives saved, the industry transformed, embody the true legacy of his contribution. Success for Nelson was measured not in fame or accolades, but in the tangible change his innovation brought about. His story exemplifies a fundamental truth. Genuine innovation is often silent, invisible to the broader world but profoundly impactful in its ripple effects across industries and lives. Ultimately, Nelson's experience reinforces a vital lesson about the nature of progress. Innovation seldom follows a smooth, heralded path. Instead, it often involves persistence in the face of rejection, the willingness to operate outside conventional channels, and the courage to test new ideas in real-world conditions. His perseverance, drastically risking comfort and financial stability to prove his concept, serves as a powerful reminder that pioneering breakthroughs are frequently born from quiet determination rather than spectacular fanfare. Nelson's work, though ultimately modest in the public eye, significantly contributed to his nation's war efforts and laid the groundwork for future advancements in manufacturing and industry, embodying, in its purest form, the enduring spirit of inventive resilience and quiet heroism. The recognition of the value of modest yet impactful innovations is a lesson that resonates across generations. Such breakthroughs often originate from unexpected quarters, highlighting that ingenuity does not exclusively reside within the walls of prestigious institutions or among top-tier experts. Instead, meaningful change frequently emerges from the everyday experiences of working individuals, those who confront problems daily and develop practical solutions out of necessity and hands-on understanding. It is not solely the purview of corporate research laboratories that groundbreaking ideas take shape, but rather in humble settings such as garage workshops where enthusiasts and tinkerers, unencumbered by formal restrictions, tirelessly experiment until they discover effective solutions. These remarkable innovations are often driven by individuals willing to stake their reputation, resources, or comfort on an idea they believe to be right, despite skepticism from formal channels or bureaucratic constraints. The next world-changing invention, for instance, could very well originate from a welder working in a shipbuilding yard, a mechanic repairing an engine in a roadside garage, a nurse finding a faster method of treatment in a hospital corridor, or a teacher devising an innovative approach to student engagement. These individuals are often dismissed by official channels as unqualified or instructed to adhere to cumbersome procedures, and yet, history consistently shows that some of the most transformative ideas come from those deemed outsiders or amateurs by the standards of traditional authority. Historical evidence teaches us that listening carefully to these voices is crucial. This does not imply that all their ideas will succeed, but it underscores the importance of remaining open to those occasional concepts that could have extraordinary consequences. One illustrative story involves Ted Nelson, whose simple invention, comprising a ceramic flux cap and a spring-loaded welding gun, epitomizes this principle. The flux cap was merely a small ceramic piece, and the welding gun was a basic device, yet, their integration led to revolutionary improvements in shipbuilding. This seemingly modest innovation eliminated the need for scaffolding, slashed production times, enhanced safety standards, and ultimately accelerated the entire process at a pivotal moment in history. The direct impact of this single invention was staggering, overseeing the saving of around 50 million man-hours, which equates to over 5,700 years of productive labor. These figures only scratch the surface of its significance. The time saved in construction didn't just mean efficiency, it carried immense strategic weight. Faster ship deployment meant that submarines could reach the Pacific Ocean much sooner, potentially altering the outcome of critical military campaigns. It also prevented countless lives through shorter deployment times, and boosted morale among workers and military personnel alike as targets were met with greater speed and precision. Beyond the immediate metrics, the ripple effects of Ted Nelson's invention can hardly be fully encapsulated. It fostered a sense of pride, confidence, and innovation that extended into national security and victory, illustrating an essential truth. The full scope of such influential innovations can be difficult to measure precisely but are undeniably profound. America's triumph in World War II depended as much on industrial capacity and technological ingenuity as it did on courage and combat skill. Soldiers, sailors, and Marines fought bravely on the front lines, but behind the scenes, the ingenuity of engineers, workers, and inventors, like Ted Nelson, laid the groundwork for victory. These innovators refused to accept inefficiency when a better way was accessible. They recognized that in a context of total war, every minute saved in manufacturing and logistics could translate into lives spared and battles won. As we confront the complex threats and challenges of the 21st century, climate change, dwindling resources, decaying infrastructure, the lesson from these historical examples persists. Progress hinges on innovation at all levels and from all sectors of society. Breakthroughs will not only originate within elite academic circles or corporate research labs but will inevitably come from working people who understand problems firsthand and are equipped to craft practical solutions. Indeed, the future may hold tremendous potential for a fitter, more sustainable world, driven by individuals who are currently overlooked. A garage workshop scientist working tirelessly on advanced solar panels, a factory worker redesigning manufacturing processes to minimize waste, or a community volunteer developing innovative methods to conserve water. These everyday problem solvers, often dismissed or underestimated by official channels, possess the essential insight needed to spark transformational change. Their ideas may be dismissed as unqualified or too simple, yet history proves that some of the greatest leaps forward have originated from such unassuming origins. Therefore, society must learn to listen more carefully and to foster environments where innovation can flourish regardless of one's background or formal credentials. Removing barriers that hinder potential, encouraging a culture of experimentation, and valuing practical, grassroots ingenuity are vital steps towards solving the pressing problems of the modern world. The next groundbreaking solution, be it in energy, healthcare, or infrastructure, might well be born in a garage, a factory, or a classroom, contributed by someone told that their ideas are insignificant or impractical. Recognizing this is crucial if we are to unlock the full spectrum of human creativity and ingenuity needed for a sustainable future. Throughout the often tangled journey from identifying a problem to actually implementing a solution, one fundamental truth remains crystal clear: some of the most transformative innovations in history have originated from individuals operating outside the boundaries of conventional systems. These trailblazers often faced opposition from the very institutions meant to support progress, because the established systems frequently resisted change or refused to listen to new ideas. Yet, it was precisely because these inventive minds dared to challenge the status quo that their ideas could eventually reshape the world. Take the story of Ted Nelson as a prime example. He began his career as an ordinary welder earning just $11 per day, working diligently in a factory. Over time, driven by his curiosity and relentless pursuit of betterment, he transformed himself into a successful industrialist who amassed significant wealth and whose technological innovations contributed notably to his nation's wartime efforts. Despite his rise to prominence, Nelson remained deeply rooted in humility, never adopting airs of importance or claiming a heroic status. Instead, he viewed himself simply as a mechanic, a man who identified a problem and dedicated himself to solving it. In his later years, when asked to reflect on his achievements, Nelson would modestly shrug and say, "I just made a better mousetrap. The world beat a path to my door." Such a statement underscores a simple but profound truth. His accomplishment was not born from extraordinary genius but from applying straightforward common sense judiciously at the right moment. When courage and perseverance are combined with practical intuition, they have the power to reshape history. Nelson's story exemplifies how one individual, armed with a good idea and the unwavering resolve to see it through, can create lasting change. What he leaves behind is not only a legacy of tangible accomplishments, such as saving countless hours of work, receiving prestigious awards like the Two Excellence Awards, or establishing a global company that continues to operate under his name, but rather, the indelible lesson that true impact comes from conviction and action. Every time a welder activates a stud welding gun, every time a ship is constructed more swiftly than previously possible, or when someone looks at an inefficient process and asks, "Isn't there a better way?" they carry a piece of Nelson's spirit. Nelson originally posed that critical question in 1941, a query that ultimately contributed to winning a significant war effort. Today, the challenge remains the same. What questions are you asking now? And more importantly, when industry experts declare that a particular feat is impossible, when government officials insist on strict procedures, or when skeptics dismiss your innovative ideas as impractical, will you summon the courage to stand firm and prove them wrong? The history of invention and progress suggests that sometimes the key to breakthrough lies in ignoring the entrenched authorities. Trusting your own observations, your gut feeling, can be far more fruitful than adhering rigidly to outdated norms. Building solutions based on that conviction can lead to innovations that disrupt industries and change lives. Ted Nelson exemplified this approach perfectly. 80 years after his initial contribution, welders around the world continue to benefit from his inventions daily. Meanwhile, somewhere, perhaps tucked away in a garage or a small workshop, a new visionary might be sketching out an idea that everyone else dismisses as unworkable. But they, too, will be mistaken because the most groundbreaking inventions rarely come from those who follow established procedures blindly. Instead, they emerge from individuals who see a problem, know how to fix it, and refuse to accept "no" as an answer. In essence, history shows us that the most vital innovations are born from courage, the courage to challenge accepted wisdom, to question the status quo, and to persist despite skepticism. It's that daring spirit that transforms a simple idea into a revolution, proving once again that the best innovations come not from compliance and conformity, but from individuals willing to forge new paths where others see insurmountable obstacles.